Hi everyone, I hope you can hear us. So I'm Mike,
I'm Catherine.
Hi. And we're going to talk to you a little bit today about something called quantum sensing and how we can use that to start making new tools, and particularly new tools for how we can look under the ground. Can you hear us okay at the back? Or are we, yeah, great, okay, very good. So let's make a start. We'll be jumping back and forth a little bit. Yeah. Okay, let's make a start. So some of you may have come across the word quantum before, or heard a little bit about quantum mechanics, quantum technology. Can anybody tell me what quantum means to them? So what does that mean? Yeah. That's right. Yeah. It's the science relating to really low energy, typically subatomic or atomic particles in physics. But why do we call it quantum? Where does the quantum part come from? Anybody come across that before? So here you see a bunch of, quite typically now we see things like quantum in kind of being used in lieu of something that's just high quality. It's becoming a bit of a buzzword for things that sound great, but it actually has a more specific meaning. Did anyone come across that before? At the back. Exactly, yeah. So actually, the reason it's called quantum mechanics it's the physics of when energy actually comes in small packets, and we're not thinking about a continuous spectrum of energy anymore in our system, but rather having small pieces of energy that come in individual packets or quantities or quanta. And that's where quantum mechanics comes from. So when we're working in that regime, special effects start to appear, and we can do some interesting things. What that means, so just to give you a bit more there, is if we think about something like an atom, normally we think about a particle as being able to have any energy that it wants. So if I had some amount of energy, I could give that particle either by kicking it or whatever and change how much energy I'm giving. But actually what we see experimentally is if we shine, let's say, light onto an atom, we can only transfer energy at very specific resonant frequencies. And for example, that can be moving electrons in that atom between different orbits inside the atom. So here what we see in the diagram is actually electrons being excited to these different levels. And on the right-hand side, at different specific frequencies, so at the bottom here, there's a red line. That's one frequency that can create one of these jumps, or the blue one's another. But in between, the light would have nearly no effect. And so that's where we start to these energy levels, and we can think about things being quantum. And that gives rise to some interesting things that now we start here being called quantum technology. So going back about 50 years, maybe it's more like 70 years now, we saw some of those being used in some early devices. But now you get some quite interesting and special effects arising into quantum mechanics, such as entanglement. So for example, if you see on the slide here, we have these two objects. The animation is not working, unfortunately, but one's blue and one's orange. Actually, they could be, we might start off in a situation where we don't know what either of those are. And it's only when we actually make a measurement on one of them that we know what the other one is. So making a measurement on one, no matter how far apart it is from the other, can instantly tell us something about the other or define its state. That's something called entanglement. But another example is superposition, where we normally think about particles being in either one place or another. But actually, in quantum mechanics, an atom or an electron could exist in a state where it's in both simultaneously until we make a measurement at the side is. That's another example, which we'll talk more about later. And finally, there's quantum tunneling. So if I won't do it, just in case I accidentally hit something. If I took this pen and I were to throw it at the wall, we'd expect the pen to hit the wall and bounce off. But actually in the quantum world, if we had a barrier, there's a finite chance the particle can tunnel through the barrier and get to the side. So some of the time we'd hit it and it would bounce back. Other times it might actually penetrate through and get to the side. And that's quantum tunneling. So that's a little bit of background, and we'll come back to some of these things in a bit. And now Catherine's going to tell us a bit about how we make these things get into this kind of regime.
Okay, thank you very much, Mike. So this is what a gas looks like if we look at it under a microscope. It's essentially lots of different molecules colliding each other with lots of random different speeds. And as you can see, the velocity is completely random depending on the particle. So temperature is actually just an expression of how much these particles are moving. If we look at this low temperature, low pressure, we can see that the different molecules have very low velocities, whereas if we look at the high temperature, high pressure, we can see that they are moving around very fast. So we can actually relate this directly to the energy of a particle with equals half mv squared, which I'm sure you guys have come across sometime in your A levels. So yeah, we can see that kinetic energy of the particle is linked to its velocity. This can actually be expressed in Maxwell-Boltzmann distribution, and if you think about it, a cold gas will have fewer particles of high velocity, so we essentially get a concentrated distribution closer to zero, whereas a hot gas will have a more spread out distribution where it has low velocity atoms and high velocity atoms. So how do we get a hot gas and turn it into a cold gas? Well, we negate the velocity of the higher energy particles. So there's three key ingredients that we need to do this with. So firstly, we use lasers. So can anyone tell me what a photon is? Yeah? Yeah, that's exactly right. So basically, light carries energy and momentum. If you look at the lights up here, it's not going to do anything to you. But for a very small particle, a photon, which is a very small packet of light, will have a massive effect on it and will impart energy and momentum, which is why we can see these balloons being popped as a laser is shone at them, because the small photons are essentially continuously hitting the surface of the balloon, heating up and causing it to pop. So this can be described as a photon, and it's basically just a small packet of light. So another aspect that we have to consider is the discrete quantum states within an atom. So as Mike said earlier, we've got the picture of the atom, and it corresponds to different energy states. So if you think about the jump between two energies, that will correspond to a particular photon, and that photon will have a particular momentum, which will, if it's resonant on that particular energy transition, you will get an excitation from one state to the other. And once it's excited, there's a random chance it will de-excite and emit a photon in a random direction. The third ingredient is the Doppler shift. So has anyone heard of the Doppler shift before? Yeah? Yeah, so like meow. So as a particle is traveling towards you, it has a higher frequency, and if it's traveling away from you, it has a lower frequency because of the wavelength essentially being shortened by it traveling towards you. So being squashed up on the way there, just like this particular particle emitting waves here. So how do we combine these to actually create laser cooling? So what we can do is we can actually tune the laser light that we're shining at a particular atom to be corresponding to that atom if it's traveling a certain velocity. So as we can see here, the dotted line represents the particular frequency of the laser. The shorter energy transition corresponds to an atom that would be traveling away from the laser, and the higher one is tuned just to the energy transition. So only the atoms that are moving towards the laser light source are absorbing their photons and therefore receiving their energy kick in the right direction. So since we can actually tune it to only the atoms that are traveling in the direction of the laser, we can slow down the fastest atoms, and we can squash the distribution of the temperature and therefore cool down the gas. So what we do in this particular configuration is we get 6 laser beams all pointing in different directions. So we slow down the atoms in all 6 X, Y, Z directions, and therefore we can cool down the temperature of the entire gas. So we have this cool gas, right? There's no use, right, if we just don't have a container of that sort, right? If we have a colder atom and it hits the side of the container, it's just going to heat up immediately. So we have to have a way of containing this. So what we do is we get a magnetic trap. So as you can see here, these are the field lines, and we've got 2 coils that are going to create a magnetic field. And in the middle, we've got a 0 point in the field. So what happens is, if the atoms are in the center of the field, they're going to be happy. But as soon as they travel outwards, this causes the energy levels in the atom to actually split. So we saw this energy level diagram earlier. So as the atom, or rubidium in this case, travels outwards, the energy levels split, and as it travels outwards, the energy will correspond to the energy of the laser that we are shining at it. So by doing that, we can essentially create a momentum kick back to the center, but only the atoms that have wandered out and correspond to that particular resonance. And yeah, as you can see, so the dotted line corresponds to that resonance, and will only receive a momentum kick that way if it's that side of the trap. And if it's on that side, it will only receive a momentum kick that way if it's on that side of the trap, and not with the other way around. So this is where we come to our demonstration. So this is a magneto-optical trap. which is essentially what I've described just now. And in here, we've got a bunch of cold atoms. So from the room temperature gas, we've actually cooled down the atoms from the speed of a jet plane to the speed of a snail. So that's the speed, the average speed that they're going at in this configuration. So this is what we can see if we look at the yeah, sure. So let's go look in here. We can see this is what you'd see if you looked inside a what, and you will see in a second. Can anyone tell me why the pool of atoms is flowing? Yeah. Exactly. So we're shining the laser light at the atoms, it's exciting it up to a higher energy state, and then de-exciting it in a random direction. So the laser light is collimated, so essentially all the photons are going in one direction. But when it de-excites, it emits it in a random direction, and this causes fluorescence. And that's where we get a glowing ball of atoms, and that's how we know we've got a lot. And yeah, hopefully we should get it.
Let's take it. It won't load, so we should.
Yeah, sure. If you guys want to see it in person, you can come see it at the end. But yeah, over to Mike, who's going to be talking more about.
Right. So that's how we cool things down. So we shine the lights on. We use photons to scatter each atom against its direction of motion. Keep doing that. Keep using more and more photons. And every time we do that, a little bit of momentum is taken away from the atom. But let's say if I go back to the idea of the classical gas now, and I made it colder and colder and colder, could I keep going forever? Or what would start to happen? There is an absolute zero, yeah. That's right. So it keeps slowing down, that's right. But eventually, we'd be unable to reach colder and colder temperature, and we get to the point where we're limited by, in this case, we're limited by the last photon the atom gives off. So it's the largest, the lowest temperature we can get to. But let's say we got around that problem, even if we kept making it colder and colder and colder, do we expect anything about the system to change, or does it just still behave a bit like the classical gas, but the atoms are moving very slowly? What would you expect? Anybody come across this, thought about this? No, good, that's fine. That's the plan. So let's talk a little bit about the difference between particle and a wave. Can anybody tell me some features that a particle or a wave might have? So give me an example maybe of a feature that a particle has. Sorry? Yeah, it has a discrete wave, it has a specific position. What about a wave? If we thought about the same thing, is that, yep. Yeah. So a wave we can think of is extending over space, while a particle is quite localized, as a specific position exists. What happens when two particles hit together? Sorry? They'll bang against each other. If they're hard particles, they'll just bang away. If they're not sticky. If they're sticky, they might stick together. What about waves? What happens if two waves collide? Yeah. Sorry? Yeah. Superposition, that's right. So we can think about particles as being very like billiard balls on a snooker table. They'll move around. We can give them some momentum. They'll go in that direction. They'll bounce against each other, exchange momentum, and so on, exchange directions. And they follow Newton's laws, so we can like write down equations that describe their motion. We can do the same for a wave, but we think of that as being continuous or extended. It extends through space. And when waves hit each other, exactly as you say, we get superposition, which we typically call interference. And we also see things like if a wave goes through an aperture, rather than just pass through, like if I threw a particle through a window, just go through the window, the wave would actually diffract and bend around the aperture. It's another thing we can see. And this again comes from interference. Now, interference is quite important, and actually we can see if I have two waves coming together, well, let's say I have the peak of two waves coming together, if you look at my fingers, then when they come together, if they pass, when they meet, they'll actually add to give me twice the amplitude that I would have had before. Or if I had two, like the troughs of the wave, they'd subtract to give me a deeper trough. But if I had a peak and a trough coming together, then actually when they meet, I'll just have nothing. And that's called constructive interference when they add, or destructive interference when they subtract each other or like cancel each other out. And you can kind of, maybe it's not very easy to see in this picture, but you can kind of see in this picture different frequencies of waves where there's like, here we can see them adding together, and in different places you can maybe make out points where there's little dips. This is actually how, if anyone has active headphones with active sound cancellation, what they do is they have a little microphone that listens to the environment around you and plays back the opposite sound to try and cancel out the inverse of the sound that you would be hearing from, say, I don't know, a digger nearby or something. Tries to play back the opposite to destructively interfere that, so you only hear the music or nothing that's being played by another microphone inside your, by another speaker inside your earphone. So that's one of the ways that those things work. And another thing we can do with interference is actually build an interferometer. We've got another one. We've got one here we can show people who are interested afterwards, but it's probably a little bit difficult to show you now. Where what we do is we can take a beam of light. So at the bottom of the screen here, you can see a little wave coming in. It hits a beam splitter, and that splits it so that it travels along two different paths. And then it travels along the paths. It's redirected by some mirrors, and after some distance, it's brought back together on another beam splitter that takes part of each of those two paths and overlaps them again. And that's a really amazing thing, because now what happens is if I were to change the length of one path with respect to the other, so if I made, you can see the mouse, yeah, if I made this path a little bit longer and kept this one the same, which I could do, for example, by moving this mirror back and forth, then what I'd see is that if I'm looking at this output, whether I have constructive or destructive interference would change. And that allows me to measure things, because now I can actually use the light. So what I'd see is my light would oscillate up and down. The signal that I have here, the brightness of that light would oscillate up and down, depending on whether I have constructive or destructive interference. And then I can use it to measure, let's say, the position of that mirror. So I could use that to precisely look at things like acceleration or velocity. And that's one of the ways which people have used to build one of the most sensitive instruments that we've seen on the planet so far. Can anybody tell me what that might be? So that's the LIGO gravitational wave detector. Uses different interferometers to actually measure, can we see a gravitational wave moving through the system with very minute changes in these two arm lengths, then gives us a signal that can actually read an output. So you can make really beautifully sensitive things with these devices. But what about atoms now? So if we go back to particles versus waves, which would we expect an atom to be? So anyone, maybe if you think of an atom as a particle, maybe put your hand up or something. Any takers? Does anybody think of it as a wave? Or what about both? Like actually, atoms can be either a particle or wave, and how they behave depends on both the state of the system and how we observe them. So you can really do things like diffract atoms and interfere atoms. And that's something that, if we go back over just about 100 years now, actually, that's when people first started to understand that was a possibility, and led to some of the biggest arguments in physics at the time. This idea that atoms, are they particles, are they waves? We saw some experiments proving they're definitely particles, and some they're definitely waves. And that led us to this idea of wave-particle duality that we see with atoms. But to observe it, that's the problem, right? So with an atom, if I want to observe it, I have to make it very cold, typically. Now, when I cool down an atom, we see that actually, the colder it gets, the longer the wavelength of the atom becomes. So not in a normal state like now, atoms moving around typically behave very like particles. They bounce off each other, they scatter around, they're just like passive gas. When we make them very, very cold, actually their wave-like nature starts to be observed. The lower energy we get to, the longer the wavelength of those atoms. And so you can start to see things like atoms interfering and so on. And if I make them really cold enough, eventually you get to a state where the atoms in this gas, their wavelength extends enough that each atom actually can kind of feel the wave of the next atom. And we go into something called a new state of matter, which is a Boseline condensate, where the whole cloud starts to behave like one big cold atom. Now, to do that, you have to get very, very cold. So we use the techniques that we've just heard about, but actually a few more. So the magneto-optical trap, this is already very, very cold. So compared to something like liquid nitrogen, we're talking about 1 million times colder than that. If we go a bit further with other techniques, we can actually enter this different state. And that's when, if I take some atoms, the cloud of atoms, I can actually split that cloud apart, bring that cloud back together. So I split the cloud into two halves, bring it back together. And now we see these fringes here, which are just constructive and destructive interference. And now, with that, we can think about actually how could we use these atoms as sensors? And that's something, this is a little bit, government been doing? That's something the government decided to start investing in about 2014. So around then and up to now, we've seen about £1 billion of investment in the UK in quantum technologies. It's not all into these atomic technologies. There's other things in there like superconductivity and ions. So there's a range of different things. But it's something the UK is really trying to play a strong role in. And this is really looking at different areas of quantum technology, exploiting different effects. So some based on entanglement, some based on superposition. Those are looking at things like how can we use quantum enhanced imaging, quantum computing, quantum communications, so very secure communications and very parallelized computing. But what we're very interested in at Birmingham is sensing. So how can we use those kind of interfering of atoms, things like that, to actually make sensors? And on our side, in particular, we're very interested in trying to connect that into applications in different areas. So my research is very focused on, can we use this in the geophysical domain? So use it to look at things under the ground. But one of my colleagues here at Birmingham is trying to find a way of using these to measure the magnetic fields that come from your brain in order to do things like help diagnose dementia, help diagnose ADHD, try and find ways to have improved healthcare for things like epilepsy. So we really see like a push across a range of different things. But our focus is really on gravity. And I can tell you a bit more.
Yeah. So the Quantum Hub research group, we mainly focus on gravity. So yeah, we actually don't know much about what's beneath our feet. We can explore the skies and the seas, but the Earth is very hard to actually investigate. So as you probably know, gravity exists between any two masses, but it's really hard to actually detect what's underground because of Einstein's equivalence principle, which essentially means you can't tell the difference between two accelerations. So if you have vibration and have gravity, it's hard to tell what's giving off a gravitational pull and what's just a random vibration. So we've actually been stunted for quite a few years in actually being able to detect what's underground. So this is what you can actually find under a typical street. So you've got, masses of infrastructure, utility hazards, and it's really hard to actually dig up without permission. It's extremely expensive. So it's underground exploration has actually been very limited. Yeah. So that's just because the Einstein's equivalence principle that it goes takes limited to 2 meters. But if we could actually look into the ground, be able to improve the speed of civil engineering projects and possibly archaeology, and we'd just be able to know a lot more about our physical world. So measuring gravity. I'm sure you guys have done this experiment before. So the way you measure gravity is you take a tennis ball, you drop it, you see how far it falls and how fast it is, and from that you can measure the acceleration. So we can actually adapt this to the quantum world. So instead of one tennis ball, we essentially have millions and millions of atoms, and we drop them. And instead of having a timer or a ruler, we essentially can just make both of those measurements with the laser itself. So this allows us to have incredibly precise measurements of gravity in very short ranges. So, like Mike was saying earlier, there's something like called atom interferometry. This is essentially light interferometry, but we switch the places around a little bit. So instead of light being bounced around a chamber, we've essentially got atoms being moved around by light sources. So the way this works is we get a ball of atoms, we pass them through a beam of light, which puts it into superposition between a lower momentum state and a higher momentum state. So as we can see, the ones in the higher momentum state are kicked upwards. So, and then another beam of light is shone at both of the atoms and switches the populations. Remember, this is a superposition. So no, each atom isn't actually in either state. It's simply existing in both states simultaneously. And then these atoms are recombined from having the same, from following the same path essentially. And we can take a measurement of them and get a diffraction pattern, like we did with the light, and we can measure the path difference between these two things. So what happens if we have a force accelerating on these atoms? Essentially, as the atoms travel, the atoms with the lower momentum, the atoms traveling the lower path will be pulled more by this mass down here, and the atoms above will be pulled less. So this will change the path length between these two arms, and from that we can find a very precise local measurement of gravity because of this basically the gradient between the top atoms and the bottom atoms. This is a little video that will show you what actually happens inside of the sensors that we're building.
So this kind of puts together a few of the things we've been talking about. So it'll just show you the experimental sequence of one of our measurements. We start off with the gas of atoms, fire that into a main chamber, and then laser beams come in every direction to cool and trap those atoms. You can't see the ones being out of the screen, so you can see anything. And then we throw that into the air, and while they're going up, we apply this process where we do a first pulse, let the atoms move apart from each other, a second pulse, bring them back together, and then a third pulse that actually causes them all to interfere with each other. So what you end up with is around 100 million individual measurements that are all little atom interferometers. So here we have one optical interferometer. This is like having 100 million little interferometers in parallel. But that allows us to make really very exquisite measurements of the gravitational field. So to give you an idea, the kind of sensitivities of these devices are now allowed to enough that if you stood next to it, made a measurement, and then moved away, the device would know whether it was there or not based on the amount of gravitational field it creates on those devices. So we can start thinking about how could we use these in a practical environment. But the problem is, even though we're using these nice techniques, vibration is still a killer. So if the ground is vibrating, that to anything looks exactly the same as gravitational effect. And that's because Einstein's equivalence principle, you can't see the difference from like being in one inertial frame or another. So what we actually see is if I were to think back to that optical interferometer, I have that fringe pattern where it's going bright and dark, constructive and destructive interference, and I added some vibration to that. What I would see is that the pattern I have is randomly scrambled up. So I end up with going from something where I have nice, clean fringes like this to just a mess that you can't really read anything useful out of it. And so what we've done at Birmingham is try to find a way of getting around that problem. And what we do is actually use two atom interferometers separated by some distance. And we use this top one here and bottom one here as separate references for measuring what the vibration is and gravity is at different heights. And then we take the difference in measurements. Because we're using the same laser beam, the same ruler, imagine just shaking that ruler and trying to make a measurement, the vibration is exactly the same for both. But because they're at slightly different heights, the measurement of gravity is slightly different. And we can then take the difference, track them, vibration is gone, we keep the gravity gradient. And that is really quite exciting because it means, in contrast to a normal gravimeter that you find commercially, where you have to measure for many, many minutes in order to find something at the ground, in principle, we can make something that can now just scan at the ground quickly, no vibration issues, and just see everything underneath the road. And that's what we've started to try and push. How can we make something to really detect things very fast? And what we'd be looking for is this ellipse shape slightly rotating because it's pulling the bottom interferometer a little bit more, creating a little bit more phase change on that one, which would slightly deform this ellipse as we move the system. But the other problem, apart from vibration, is this stuff is historically very large, very expensive, very costly stuff that uses a lot of electricity. And we're coming from really laboratory science. So here what you see on the left-hand side, that's the setup that you need to make one of these fog clouds, or that you needed 10 years ago to make one of these fog clouds. In addition to that, which is a lot of optics, lasers, vacuum systems, and so on, you need full racks of electronics to control them and keep them all running. So that's what we're kind of coming from. But in the group, what we've been really trying to push is, can we make something that's much more compact, robust, and can actually be used in a more realistic real-world environment? So we've done some innovations in how do we deliver the beams into the chamber so that if the intensity of the lasers changes, it doesn't destroy the cooling process. We've found ways of making the lasers much more compact. We've actually made systems like this where now, rather than having to come to our labs to see it, we can actually take these things to events and show people this is how laser cooling works and so on. And we've even got to the point where we can fly them. So we've had a system now that weighs about 4 kilograms, and all of the things we need to do to make laser cooling happen can be done in a little drone flying around on the battery. So it starts to really become a lot more practical. But we still had to think of a good way of making a full sensor out of that. So we found a way to make something, this gravity radiometer, patented a new technique for doing that, where we use these, you can see these little, if you look on the right-hand side, these little blue mirrors to actually divert all the beams in the right way. That led to a patent which actually proved we can make this thing very robust. We can use it for for months at a time without needing to tweak the knobs inside to make it keep working. And we subjected that to some really quite challenging conditions. So you can see on the left-hand side here, We took that into a cave to kind of assess how well will it work in like quite cold, quite deep and wet and damp environments. And we started to do surveys where we can actually survey over roads and learn about all the things that go wrong, how magnetic fields influence the instrument and so on, in order to try and make something that can really be used in a practical setting. And so what we did in March last year is we actually took that just behind the music building, so just over that way a bit, and moved it across a road, trying to detect if we could see some of the underground infrastructure. And we got it to be sensitive enough that we can start to detect tunnels underground. So what you see here is if I start the sensor kind of over here, this position, here we read quite high gravity gradients. And as we move across the road surface, I'm moving to the right here, in the middle, there's less mass under the ground, so we see less fall. And that's because there's no soil there, there's a tunnel, so there's a hollow, and that's something we can start to see. And using that, we can start to detect these underground infrastructure and say where it is to within about 10, 20 centimeters. Which means, for example, that now when someone's trying to fix a pipe in a road, roughly 3 out of 5 times they dig in the wrong place because they don't know where the pipe is. This could mean actually we can see the pipe, we know where it is within 20 centimeters of thing. We could rather drill down rather than digging a big trench and hopefully create less road congestion in the end. That's where we're trying to push to. And the kind of things we could start to see, so with everything that's kind of in the green area here is stuff that our sensor could in principle see. It has that kind of sensitivity. Things like tunnels, things like buried utilities, but the one I'm probably most interested in is archaeological sites. So we work with people in archaeology in Bristol and Bradford, and they have been doing surveys with conventional gravity sensors to see what can they see under historic and heritage sites. So for example, most things like Stonehenge, you typically find that ancient civilizations found that to be a very, for whatever their religion was at the time, a very culturally significant site, and they tend to have their history accumulated around there. Typically, they find underneath those sites more history of other sites and so on. So underneath some henges, they found older henges. And recent survey, not that recent now, but surveys have shown there are blobs underneath some of these. They can see blobs, but they can't see what they are underneath these sites because we can't dig them up, right? We can't dig up Stonehenge because it's destroyed. So the only way to look is really to develop these kind of looking through the ground technologies. But in the future, we're hoping to be able to use that to start looking at things like, can we actually detect drainage for railways and telecoms to help get utilities better towards homes and so on. And this actually opens quite a lot of applications. So now what you can see on the right-hand side is just an example of what the kind of maps that we can create could look like. So in the middle, that's what things look like at the surface. And then we have a map of the subsurface underneath. And the top is a simulation based on the noise we have in the instrument of what actually our gravity maps could look like. So you can start to see that it's quite easy to see things like tunnels. It's quite easy to see things like building foundations and archaeological features. But it's still a little bit harder to see things like aquifers, which are very important for monitoring how much water there's being used from those sites. And it's quite becoming possible to see things like where do we need to plough fields to improve the yield of our crops and so on. So it starts to be useful for these kinds of things. And the other quite interesting or exciting thing I find is actually we could use these as a way of navigating. So one of the ways we typically navigate is using something called GPS, which relies on having access to satellites. But if we could instead have a map and use a gravity signal to actually position where we are on that map, it allows us to navigate in new regions where you can't always look where you're going and so on. So this could be quite exciting stuff. And the other quite exciting use we see for these technologies is actually back on the fundamental science side. So if we can do things to make these devices more sensitive, so to give you an idea, the current instrument we have stands about this tall, but if I want to measure the gravity gradient very sensitively, the further apart those two sensors are, the bigger the difference would be in gravity pull between the two, bigger signal. And what we want to do now is start thinking about, could we build systems that aren't a meter long, but more like kilometers long? And can we, rather than splitting the cloud apart by just a small amount, actually create superpositions that are many, many meters apart to make these things really, really sensitive? And that now is conjectured as a way that we might be able to use sensors to start looking at future gravitational waves and maybe start probing certain areas of the dark matter spectrum to see, can we help aid with searches of those kinds? And so what you see here is just like some of the laboratories we now have set up at Birmingham, where we're working with universities across the country to try and build the first generation of these large 100-meter to a kilometer long devices, which we hope to see coming in the next 20 years or so. And I think that is everything we had to say, but we have these things we're very happy to show people if they're interested. So thank you very much for coming.